we're going to change modes here. Bill is, as I said on the website, I'm co-editing a book, and Bill is one of the chapter contributors for that book, and we're looking forward to hearing about the chapter in this talk.
Well, thank you all. You know, if you come and talk to astronomers, you know you're not going to have the prettiest pictures in the conference. This work is somewhere.
Who's Google?
Who's Google? This work is somewhere in some boundary between things that are established in the literature and it's kind of a personal assemblage of ideas out there. I thought to have some chance of making it interesting for an audience that has astronomers, that I would try to connect it with some astronomers. Some of them are listed here. You know, these are people that have multiple fields now claim them as their antecedents of Gauss, of Bessel and Poisson. And I found it quite easy to connect with these, and I hope you enjoy the talk, if not the pictures. All right. Here's the abstract as written, and I've made some attempt to gloss it over here. This is in the category of general linear models, and the particular emphasis here is what we're going to call conditional likelihoods. These are likelihoods on the response. As one might speculate, there's a combinatorial issue with conditional likelihoods, and that sets us up for an approximation which I kind of think physicists would claim as, I thought of that maybe decades or centuries ago, but it makes for kind of a path forward here. So here's the general outline. There's going to be some notation, and the simple models are the exponential family. The second bullet starts introducing some of the meat with conditional models and what I'm calling chunking here. Chunking has a lot of synonyms, but this is one of these cool Anglo-Saxon words that I'm trying to pull you in with. The spherical approximation that appears, and then toward the end, I compare it to some other four-letter acronyms. The basic data structure is like this. I'm going to have a response, and I'm going to use the letter Y. The predictors, I'm going to use the letter X. Statisticians in these modern times have to be bilingual, and the word predictor in some areas it gets called feature. So at Google, just that's what we call it. The statistician term is something like predictor or covariate. We're going to estimate something like a linear model here, and so the coefficients are uniformly beta. The greater formalism is there's some probability model, and so in this sketch of the data structure, kind of the fuzzy part, please don't pin me to this, is that wavy equal sign. It's just to motivate, but I was just too lazy to write the function f or something. So these are some models that are kind of in the background here for motivation. I hope you recognize some of the names. They're my friends, but they're probably you guys' friends too. So the Poisson is a distribution on integer. The Gaussian, of course, is over the real line, and the logistic distribution is, it just has two states, 0 and 1, and the shape of the curve is this sigmoid. So the point of these models is they're pretty, and you know, a few decades ago, it was recognized that the prettiness could put them into a single family, as one might expect. And so this is this so-called exponential family along here. One way to think of it is, here's a term where the data interact with the model, and that's this yellow bar, and denoted by H0. Managing kind of the domain that the parameters fit over is, say, H1, and then managing the domain that the response is over is reflected in H2. And so in this table is particular realizations of how each of this cast of characters of three distributions fit into that larger family. So it's one of the traditions of math and maybe statistics to go to some more abstract and general level, and that's what we're doing here.
Where in the natural world does the logistic distribution appear?
Well, it turns out it's my best friend. Okay.
So it's important to ask.
It's important to Google, where we secretly think we have the largest logistic regression in the universe. That's kind of the way they talk there. And I'll tell you later what they call it. But, it helps in this context because it's actually kind of an extreme version of the Poisson, you know, because it's like taking away the counts of two or more in a certain sense, and so it has for the average it has kind of the largest standard deviation in some sense. The person associated with the logistic distribution, by the way, is a sociologist, just in case you really want to kick it out of the conference. All right, so maybe you can invite a census person to talk about his 2 terabytes of census. You get no cred here. All right, so here's actually kind of a foundational idea in statistics, and it's my particular delight that it's associated with mathematician astronomer Bessel here, where he noticed that if he compared to his neighborhood astronomers, colleagues in other parts of Europe, that they would have, in effect, a systematic error measured in arc seconds. Okay. And so this, he coined the term a personal equation. So somehow the instrument, which is the astronomer in this case, kind of has its set point, and that you can characterize it. Here you see, so like Wallback versus Bessel, that's a difference of about 1 second, and that it's got this transitive property here. So this is kind of one of the surfacings in the history of data and statistics, the notion of having a control group. Maybe Galileo dropping a big weight and a small weight and at the same time is also kind of a notion of a control group that's concurrent. But here's the most tangible manifestation of it here, and it motivates us talking about chunking here. And so in chunking, I'm going to, in effect, have a label that will partition my data structure. I'm going to index it by G. G stands for group, because I have plenty of other uses for the letter C. My apologies if this seems too much like Sesame Street, but that's the data structure, is to recognize that there are chunks. Now, chunks are both important and strangely controversial to my universe. But let's see why it might matter. Well, for the kinds of models we might do, and remember I'm just kind of being very vague about what the funny equal sign means, but there is a chunk-specific effect here, and that's separate from maybe the stuff we care about. And the way chunks come about is, in the Bessel context, it might be something like a single observer, or a single instantiation, or a field of view, if you allow me to pretend that I think I know what astronomers do when I say the word field of view. But the other thing you can do with a chunk is you can have a single entity pointed at two different times. You know, so like you point it toward the galaxy, and then a month or a year later, and you point it at that galaxy, and maybe you have a computer and you subtract one image from another, and there's this bright spot, and you call that a nova, right? You know, so that's the other way of chunking. The point here is that if you ignore this kind of chunking effect, then if you have some response function, and if you ignore it, it's the price of ignoring a feature, and by ignoring it, it's something like averaging it out, and you created what's called attenuation. You know, so your model is not so acute, and that sets you up for lots of trouble. I happen to be Mr. Attenuation at my day job. I don't know. Do astronomers have day jobs?
So are astronomers.
Reducing our
Okay. So in the first two talks, by the way, there was a moment of truth there, because the statistician had the lights turned on and the astronomer had the lights turned off. All right, I've softened you up. Okay, now condition here. So if you write down a likelihood, it's going to be this kind of expression where you're going to say, well, the groups are independent and maybe the observations within the group are independent. If you condition on that, what will you condition on? Well, in this context, conditional models mean if this is my group, then let's see, what do I have? I have like 7 zeros here, and I have a couple of ones, and I have a couple, yeah, I have a 2. What I'm going to do is I'm going to condition on the histogram. So I'm going to condition on the fact that in my chunk of 10, I have 7 zeros, 2 ones, and a 2. Okay. But I don't know exactly which row gets which. So that's why there's still information after conditioning on that part of the response. And so this can be rewritten if you admit that I can rewrite this now in kind of a micro vector format. And whereas I guess if I were at Google, I would have to show that I'm permitted. I'm doing something terrible. I'm running down on the battery of this laser pointer. But right here, you've got an index. So that's reflecting the permutation, the permuted index there. But statisticians like matrices. I think we're kind of one of the main consumers this past century of matrix theory. And so this can be expressed as a product where this is a permutation matrix. Okay. So I kind of hope you get used to the notation, because I'm going to smile on the next slide about it. So in the book, we kind of go from, here's the conditional likelihood, and then it's as a function of these parameters, eta, but these are, if you will, the latent features, and I'm assuming that they exist here linearly. So that's really almost just an expression of notation. But it turns out in the exponential family, remember there are these three terms, H0, H1, and H2. That's how C programmers count too, three terms, 0, 1, and 2. But it's only the H0 term that still stands, so that's kind of pulling you along toward something elegant going on here. Because this means that this is literally the same expression for the three distributions I flashed before you, the Gauss and Poisson, and the logistic. And so if you do one more step and just allow H0 to be chosen as a linearized form, then it takes this bottom form. All right, so there's something elegant going on if you have any aesthetic for computation, where you probably can all outdo me at. This is one of these things that nobody volunteers to do because it's a combinatorial denominator right down at the bottom. Okay. You know, you show one of those at Google, you probably just don't get hired or something. But you know, hang with me a little bit. Let's just motivate to see how chunking does by considering the case of the logistic distribution here. This is the unconditional form. But if you just have a chunk size of 2, which is kind of what happens if you taste tea and then you taste a different cup of tea and you decide which one's better. That's how people really cope really well. You get a choice of 2. So it's a good source for such pairing. That with a little bit of work, this conditional logistic gets rewritten into this form. And this is intriguing in its own right, because you have, well, you know, this is either a 0 or 1. And so if they're both 0s or both 1s, you just throw out the chunk. Okay. And in fact, this is a general property. If in that chunk you've got all 0s or all 1s or all of the same, you just throw that chunk out. And you don't know, well, you do know, but that can lead to a big simplification, because all of a sudden you've gone, you know, down by maybe a factor of 10 in your data set just by considering chunks that only have some contrast to them. The other thing going on here is you've now got, by doing chunking, one of the observations can be like the control. So now you've got, if you will, in this family of models and in the style of thinking, you've got an expression that in the math themselves, it tells you kind of what to do for the control group. And so you're not having to force that in from the outside. I thought about trying to get a picture of my middle school science teacher, you know, the one that tells you that you have to do your control group at your desk, and you can't borrow the control group from that smart girl across, you know, on the other aisle, right? It's the same aesthetic that's showing up here with the concept of chunking, and the math pulls you along that way. Okay, so maybe you guys are all good, but maybe you're kind of wondering where the gristly part of the talk is. I've already talked about the scary part, because there's this permutation part. So you're just rewriting the permutation likelihood, and so that's a sum. I'm recasting it the way that statisticians are comfortable recasting it, by talking about it as an average of something. here's a little piece of geometry in the case of having three objects. Three objects actually live in a two-dimensional subspace of 3D, and I tried to indicate it here. And so they form that regular object of a hexagon. So these. Now, the approximation I'm going to do is this, and I'm going to get so excited about it, you're going to feel like I'm never going to talk about anything else, and that's almost true. I'm going to take this averaging over permutation, I'm going to, which is a group, and I'm going to replace it with the orthogonal or rotation group. And so that's rather like, you can kind of see a certain kind of physical intuition here. This is a model of benzene, of course, and so you have these 6 carbon atoms here. And if you go out far enough, you see the atomic structure, but kind of this inner radius, it looks rather circular-like. And so we might want to just park that piece of physical intuition because it's relevant to what happens. Also, here's a little piece of SDM of graphite, and you also see both the atomic structure, if you want to, at the right radius, but the inner circles you see circles too.
Wait, can you always take the n factorial permutations of n objects and turn them into a regular polygon and instead of summing over the permutations integrate over
Well,
permutations? Is that what you're doing?
that is what I'm doing.
And that's always possible?
Is it always possible? Well, it works actually better for when the number of objects is big-ish rather than 2-ish. And as you might infer from the diagram of benzene, it's going to work better for small radii rather than big radii. I mean, just to answer your question intuitively. Okay. But permutations are a group, right? Mathematically, so that's an expression of symmetry. And rotations, they're a group too, and they're an expression of symmetry, and the permutations live inside them. And I say those words just to reassure you. I figure if I say group theory a few times, that's kind of the pixie dust to get forward. Am I right? There is another level to your question. I mean, to the answer to the question. Okay, now, one of the, I wondered about whether to do a slide here, but it's really because of this ratio is invariant to what the response sums up to, or for that matter, what the model part sums up to, that I can just make them both equal to 0. And so that will be implicit in everything that follows. The spherical approximation is known in statistics as the von Mises-Fisher distribution. Von Mises actually just proposed it for a circle. And Ronald Fisher proposed it for a 3-dimensional sphere. The people that generalized it to a hypersphere are Watson and Williams, but they didn't get it named after them. It's a little bit of a vestigial distribution because it's got the equivalent of a circular error probability. It's just that it's on a sphere, right? And so a statistician would say, well, where's the covariance structure? How come I can't go ahead and do an ellipse or something like that? So it's not talked much about. At any rate, the combinatorial, what would be the combinatorial denominator, the normalizing coefficient winds up being a Bessel function. And so that's relevant for what follows. And it's actually kind of the main reason I put Bessel in the title of the talk. So there's going to be a double notation here, but probably everybody in the room knows Bessel functions better than I do, and that was certainly true a few months ago. But the Bessel functions have a scalar parameter, which in this context is kind of like a radius. And the radius has two parts. And the two radiuses are the standard deviation of the data, more or less, and the standard deviation of the predictors. And see, this parameterization can kind of exchange a multiplicative constant from one side to the other. And so it seems reasonable that this parameterization, because it can share a multiplicative constant, I hope you feel like it looks like the right thing. Let's see. So, and then in this formulation, this is set up as on the unit sphere, and the direction is with this unknown parameter mu, and then the radius is this kappa. So that's at least for the two books I was looking at the time, that counted as standard notation. And I felt like, since I was at risk of being confused, I kind of wanted to keep to some standard record. Okay. So to use these ideas, we want to be able to estimate something, and that means calculating the gradient of the likelihood. The gradient of the likelihood is going to depend on this part, which is just the data, and then you're going to have in here a factor which corresponds to the mean of the von Mises Fisher distribution, and it winds up being this ratio of, well, modified Bessel function. Okay. And so, so this notation here is what's this ratio rho is what's really going to play a role here, and we're going to deconstruct it somewhat. Notice here you have that that product of radius here, but since this part depends on the unknown parameters beta, kappa 2 does, but this part does not depend on it. And so that's part of some interesting piece of algebra that happens. If you characterize what that ratio looks like as a function of kappa 1, this looks quite a bit like just the variance of the data. As a function of kappa 2, the variance of the prediction, with the exception of a chunk of size 2, it's got only a weak dependence on that. And so this is one of these weird moments where statisticians are talking, and we get excited about a plot that has no signal in it, because that's how we do goodness of fish. Is we say, look, we do this plot, and since we don't see structure, it means the model's good. And so here, to the extent that there is no structure, there is no strong dependence on kappa 2, this gives us some computational advantage. Okay. Thank the few of you that are still smiling about that. Okay, so there's a way of reparameterizing this expression, and it's to say that, all right, let's imagine this r squared as kind of a shrinking of the data part to and if you reparameterize it, this winds up being very familiar to statisticians because this looks very much like the Pythagorean theorem as statisticians practice with analysis of variance. Because here you have what the magnitude that's in the data, and here's the magnitude that's in the model. in the context of our classical theory, which is linear models, this will always be smaller than that. It's not true in these general linear models, but forget it. And this ratio is what we call R squared with capital R. It's the multiple correlation coefficient is what it is. So part of the intriguing thing is that this model kind of uncovers a certain kind of multiple correlation coefficient. You would kind of, the math kind of forces you to invent it. I didn't invent it. Okay. And then I thought it was appropriate to work out an intuition for what this ratio looks like numerically, sort of like what I did on my Christmas vacation or something. And it's bounded. It's dominated really by the variance of the data, and the role of this other stuff is smallish. So this is it's in this sense that because it's a weak function of R squared that it's numerically interesting. Okay, so if we calculate the likelihood, I hope some of you were already tempted by, well, when is he going to set it equal to 0 and solve for stuff? I kind of hope at least some of you were thinking of this. And so it pulls you into a set of equations that look very much like Gauss's so-called normal equations. All that's really happened is we've created this extra little factor. That factor, by the way, plays an important role because what it does is it says if in a chunk you don't have information, or if it's low information, it's going to discount it. That seems like a worthwhile thing to do with a chunk. Also, because this ratio depends only weakly on R, and that's the only dependence here really on the coefficients beta, you have fast convergence. And finally, it winds up being, R winds up being kind of a measure of the prediction strength of the chunk. So that's pretty interesting. Let's just see some data how it works. Here's the first iteration of, so this is chunks of size 2. This bottom row above the lines is this algorithm with no iteration. You just pick a correlation, you run with it. Chunks of size 2, you actually have some exact estimates available, and that's the top line. So you get quite close with that. Also, there's an iterative method where you modify it. You have two objects, but you're kind of in a one-dimensional space, so maybe you can tweak the order of the Bessel function to reflect the lower dimension. And that gives you estimates that they're not explicit here, but you get like 4 digits of accuracy. You kind of feel like you're looking at a theorem here. Whereas this is more like 1.5 digits that look the same. Okay, so that's one example of some data. See how that says feature 1, feature 2, feature 3? I do stuff like that so that Google lets me publish data. You knew that. Okay. Here's another set of data. These are some humans. There were 223 humans, and there are about 8,000 tasks or data rows here. In spite of that, combinatorially, this square here is kind of out, which is most of where the data is. The chunk size is too big, and there's too many ones to feasibly fit like benchmark conditional logistic regression exactly. But you do get quite good estimates without iterating, and then with iterating, only a couple of terms move up a little, but you're definitely in the ballpark there. Okay, so a couple things that are related. In the main standard here for calculating general linear models is this iteratively reweighted least squares, and you get equations that look like this as a function of the weights. The weights themselves are functions that are of the parameter space, and for that reason, because the weights are a strong function of the parameters, the convergence is not so fast. But it's of that family. Notice here the weights belong both to y and x, and they're the same here. The weights kind of cancel on the right-hand side for the spherical estimate. Okay, here's something similar. It is a way of using r squared, and what you do is you form cumulative sums of as a function of the chunk. You do cumulative sums of the variances of the fit and of the data themselves, and if you plot them one against the other, the slopes anywhere along here are how the local slope is kind of a property of how good the fit is for that kind of chunk. And in this case, what I've done is, it matters, of course, the order in which you sum these things, and I've sorted them by the magnitude of this quantity. So these are the low information chunks, and you get a better fit there, and then you have the larger information chunks, and you get a differential witness of fit there. I don't know about you guys, but do you ever sit in these meetings and you get, well, here's the output of my model, and you kind of want to deconstruct these estimates into different parts of the data. So these numerator-denominator plots are one way to do that. Third thing to do is the people at Google say, well, that's very interesting, but I kind of have a billion features, and just between you and me, they don't want to invert a billion by billion matrix, which is kind of what this would involve. And so there's something called marginal regression, which is you basically you run each single feature against the response separately, and that sets up for a certain kind of map-reduced style parallel computing, and then you just pick the big ones. The spherical version of that also works. What's interesting is that it sets you up for an iterative estimate. This is just housekeeping to get an algorithm going. This is an update step down here. This is a projection to filter out. This is a projection that filters out what you've just learned from the previous step, and so that sets you up to do a reasonably scalable many feature. I suspect from your posture that I better hurry up. Yes. Yeah. Okay, everybody. Michael leans forward. Okay. So something that's kind of a natural consequence of these conditional models is you can fit them, but for instance, you don't have a natural intercept term. That's the coefficient of the constant feature, if you will. And so there is a second algorithm to do that. Also, in order to calculate, to correct for attenuation and even for the Gaussian, sometimes you have to do a slope on the single feature, which is this overall feature combined. Just that new feature z, that's a one-dimensional feature, but to go get a coefficient for it. So this is an interesting framework for making these multiple stage models legitimate, and that's interesting in its own right. So here's just a summary page. The basic framework is this linear predictor space, and then the so-called generalized linear models. and then the chunking stratified sample. So that's the general framework. Here's a list of problems that we're dealing with, mostly the nuisance effect from attenuation, but also the combinatorial denominator. We get this spherical approximation. And we get some algorithmic help here that works out pretty well. Here's some characterization of about the algorithm itself and some things that maybe I could talk about more. I have 2 more secret slides, but shucks, if no one asks the question, why should I show them? So I'll just ask if there are any questions for my breathless state. I'll stand over here to see if there are any new faces on this side of the post.
Okay, thanks, Bill. So any more questions? No, I guess you can show your secret slides.
So, probably on purpose, you said nothing about how Google uses these sort of applications. Can you say anything about what you're doing with them and you know, sort of data handling that you're applying to them?
Well, Google has a feature called image search, as you know, and the guy that's bugging me the most about having billion feature vectors has been working on image search. The main application for things like logistic regression at Google is with serving ads, because there's an auction process where advertisers will pay so much money if someone clicks on their ad, and then if we know the probability that they click on it, then there's kind of the money, kind of the probability of getting a click, and that's in the guts of our advertising system.
Okay. All right. Well, thanks again, Bill. Great. Thank you.